Hello everyone, my name is Li Shuyang. I'm from City University of Hong Kong. The topic of my presentation is a comparative study between daylight factor-based metric and other daylight metrics for daylighting design. There are 6 parts in this presentation. The first part is introduction. Hong Kong is the most densely populated and built-up city. Nowadays, over 90% of electricity is consumed by building sectors. Daylighting is an impressive and sustainable development strategy. A good daylighting design can enhance visual comfort, physical health, energy efficiency, and green building development. In order to predict the daylight performance of room space, researchers put forward a number of design metrics, such as daylight autonomy, useful daylight illuminance, and daylight factor. Nowadays, daylight factor calculations have been extended under all sky conditions. It means that daylight factor-based metric is no longer static. This research compares the daylight factor-based metric and the dynamic daylight matrix. The second part is daylight matrix. The minimal daylight autonomy is the percentage of year when a minimal illuminance requirement is met by daylight alone. However, it cannot reflect excessive indoor daylight. To deal with visual glare issue, maximum daylight autonomy is proposed. As a basic modification of daylight autonomy, the continuous daylight autonomy is the fraction of occupied hours per year where the illuminance at a point is greater than or equal to a target threshold value, and where partial credit is given where the illuminance is less than the threshold value. Spatial daylight autonomy describes the percentage of floor area that receives the threshold illuminance for a standard percentage of the annual occupied hours. The useful daylight illuminance is defined as the illuminance at the work plan within the range of 100 to 2000 lux. The UDI can reflect the natural lighting distribution in different illuminance intervals and can be used to predict the glare conditions of indoor space. The point daylight factor can show the energy saving of daylight-linked controls. The average daylight factor is directly related to window parameters, and it can be a useful daylighting criterion. The vertical daylight factor can be used for compact urban areas with large exterior obstructions such as Hong Kong. The third part is case study and the proposed methodology. This figure shows the room layout for case study, and there are 9 reference points in the room. Window area and transmittance are the 2 variables. These 3 equations were used to calculate the PDF, ADF, and VDF. Based on the measured sky luminance data, the best fitting sky luminance distribution approach is used for sky classification. This figure shows the results. The sky 1 to 5 are the overcast skies, the 6 to 10 are the intermediate skies, and 11 to 15 are the clear skies. We can see that the sky 1, 8, and 13 are the typical sky conditions in Hong Kong. As shown in the figure on the right, the skying angle is the shortest angle between the sun and the window normal. The figure 3 shows the correlation between vertical daylight factor with skying angle on the overcast sky. We can see that for sky 1, 3, and 5, the VDFs are independent of skying angle. On the sky 2 and 4, the curves vary gently. All measured VDFs are well fit under sky 1 to 5. For intermediate and clear sky conditions, The VDFs vary substantially with guiding angle. The largest and lowest VDFs are both occurring in sky 15. The correlation of VDF and guiding angle indicates that VDF is an important parameter for building orientation designs. There are 5 cases with different ADFs under sky number 1. Results from different window area and transmittance. As the window area and transmittance increase, ADF rises gradually. It means that ADF can be opened easily by changing window area and transmittance. This table shows the ranges of average daylight factor under 15 CIE standard skies. Under overcast sky conditions, the change of ADFs in each case is not obvious. As the window transmittance and the area increase, the ADFs become larger. It will not only cause visual comfort, but also will generate a large amount of cooling load. Similarly, the ranges of point daylight factor under 15 skies are shown in this table. The minimum average point daylight factor are found to be 0.8% at 0.6 and 9 for case 1, and the maximum average point daylight factor is 14.7% at 0.1 under case 5. Point daylight factor can be obtained by timing the point daylight factor with the horizontal diffuse luminance. It means that PDF can be used for calculating the UDI and different forms of DA. This table shows the useful daylight illuminance at 9 reference points when the ADF is less than 2% under sky number 1. The daylight illuminance in the range of 100 to 2000 lux account for a high proportion of annual daylight illuminance for 9 points. It means that the indoor daylight environment available for people to live or work should be neither too dim or too bright to cause visual discomfort. When ADF is more than 3%, points close to window get more excessive daylight and are more prone to glare, where the points further away from the window receive less daylight. This figure shows the comparison of daylight autonomy and continuous daylight autonomy. The daylight autonomy is generally less than continuous daylight autonomy for all cases when ADF is less than 2% under sky number 1. These two daylight autonomies can be used for evaluating the energy savings of dimming or switching daylight linked lighting control system with different target illuminance settings. For spatial daylight autonomy, when ADF is 1% under sky 1, the values of spatial daylight autonomy are below 50% because of the small window area and low transmittance. When ADF is more than 2%, the values of spatial daylight autonomy 50% with 3 target luminance are equal to 100%. It means that 50% of total occupied hours may be too small to evaluate the annual daylighting performance. Here is the conclusion and discussions. Different forms of daylight autonomy and useful daylight illuminance can be computed by using the daylight factor of a particular point. The criterion 50% of the total occupied hours for spatial daylight autonomy may not be appropriate to evaluate the annual daylighting performance, as the 50 CIE skies represent the actual skies for many places and cover the whole probable spectrum of skies found in nature. The daylight factor approach could be globally adopted and would be useful to practitioners engaged in architecture and daylighting designs and evaluations. The further research will conduct these 4 works. That's all, thank you.